We will speak in meeting 12 about the Internet of Things. Internet of Things definition are varied, but generally they express the idea of digital devices exchanging information between each other, although not necessarily over the internet. So no need for the internet in this case if we have Internet of Things. Early name for the Internet of Things was machine-to-machine communication. As long as you have some type of connection between the two devices, they can exchange the information between them, then you have Internet of Things. Some Internet of Things applications are already well established, like, for example, the credit card readers in shop are very familiar, where we have some reader of the machines there, where you place your credit card on the machine and it will read the information stored in your credit card. More recent example is the so-called smart meter, which is smart devices like the TV, the washing machine, the refrigerator, the phone. So any smart device that can have internet and built inside it. It is an electricity meter. So what is Internet of Things? How it can be defined? It is an electricity meter that uploads its own reading to an electricity company, removing the need for a meter reader to call occasionally. You can't see the screen, so just wait. I will check what's the okay. Sorry. Just a minute. I will fix the problem. Just a minute. So I will leave the meeting and come back. Welcome back. Can you see the screen now?
Yes.
Very good. So here, what is the smart meter? It's actually electricity meter that uploads its own reading to an electricity company, removing the need for a meter reader to call occasionally. So there is no need for a reader. They can send the signal between them. The Internet of Things is expected to become really innovative only when it's supported by automated intelligent process. So it will have some processor to manage the signal. With the addition of automated intelligent process, the Internet of Things could change manufacturing, commerce, and home life. Like we have now the smart homes. So we start to have smart devices around us that can communicate in distance. In fact, the term Internet of Things is often shorthand for a new era of technology's progress in which familiar objects and services, such as household appliances, cars, public transport, and so on, become smart. So they can be connected with each other's exchange information without the needs of the internet. And today, meeting, in meeting 12, we will focus on the communication technologies required to make Internet of Things possible. So we will look about examples of Internet of Things applications in industry, business, and at home. We will look on representation of data as binary numbers. We will look about features and the problems of radio communication. We will look about the requirements of Internet of Things data network, like the cost, the data rate, and transmission power and range. Radio networks for Internet of Things traffic. We will look on power and energy consideration and home automation. So here, a possible case for Internet of Things we can see are already established around us. We can see it in utilities, in gas, water, electricity. We have now smart meters, automated meters reading system. We have smart supply grid. We have management and the tracking of assets, resources, and the products. And smart cities, we can find the Internet of Things on the traffic control, on parking management, on lighting control, in waste management, and environmental monitoring. So all these types of Internet of Things. In healthcare, we can find it in fitness tracking. Like, for example, if you hold your phones, it can tell you how many steps you already moved. If you do any body activities, it will tell you you already did running or jumping or swimming. Like the smartwatch, we can have also the patient self-monitoring and remote monitoring, like the heartbeat system, the sugar monitoring. In transportation and automotive, we can see it in connected networked car, road management, in tolling and speed enforcement system. We can find it in vehicle platoon and autonomous vehicle. We can see it in connected trains, boats, and planes. We can see it in road and rail asset tracking and management. In retail, we can find it in goods tracking, shelf life management, and inventory management. We can find it in automated shelf pricing, customer browsing data. We can find it in shelf compliance. So this is our examples of where we can find smart ideas, smart things. Internet of Things applications involve taking reading from sensing devices distributed across an environment, like the traffic lights or the speeding camera, and sending this data from these sensors periodically to a server. So it will collect which cars have speeding across the allowed speeding, and will send the data to a server or computer at a central base, where the data is collated and analyzed. So it will analyze from the plate in the car, which car has speeding and in which route and which time. Sensor information could include, for example, reading of temperature, humidity, speed, light level, noise level, occupancy. For example, whether a car parking space is occupied or empty. And you can notice in some of the car park here, they start to put a light on the top of the roof where it has green if there is a free space, or it's red if there is occupied space. Here we could have three questions present themselves. How much data traffic is likely to be produced by such devices? And are there special requirements for such data, such as timeliness, accuracy, security, and confidentiality? And also, can this data traffic be accommodated in existing communication network, or are special network required? Do we have to make a special connection network for this data, or it's already can use the existing network? Here, for example, data for the Internet of Things. Suppose a device records the wind speed at a location. So we will measure the wind speed in a specific place. The wind space reading could be represented as binary numbers with using 4 digits of binary numbers, 4 bits. Here, table 1 will show us the increased wind speeds and their binary equivalent. So if the speed was 0, the binary equivalent will be 4 zeros. If the wind speed was 15, the representation of the binary equivalent will be 111. Sorry, 411111. Here, this is because the table use 4-bit binary numbers to represent the speed. This means we could have 2 power 4 different cases of representing the speed of the wind. So the lowest will be when all the 4 bits are 0, and the highest will be when all 4 bits are equal to 1, which is equal to 15 kilometers per hour. In general, if we use binary numbers with n bits, so the maximum data that can be represented with this n bits will be 2 power n. So if we have 7 bits binary numbers, the maximum numbers of data to be represented with 7-bit will be 2 power 7, which is 128 different speed or different data. A speed of 0 is one of the speeds represented, and the highest speed representation will be 127 kilometers per hour, which is equal to 2 power 7. The previous question raises a way of thinking about binary numbers that might seem strange, but is quite common. The number of bits in a number can be thought of as a way of quantifying information. So we can imagine which type of data can be represented here. Suppose that we use the additional 3 binary digits in the question, not for representing higher speed like 127, but for more precision than was possible with 4 binary digits. So we will use 4 to represent the speed of the wind, whereas the rest of 3 to represent 7 bits in total to represent the fractional part of the speed. In this case, we will have the maximum number to be represented here as binary when the 4 digits is 1. Whereas the rest of 3, if they are 1, will represent the negative power of 2, whereas the 1 after the decimal point will represent the half, the 1 will, the after 1, the fifth one will represent the quarter, whereas the 7th one will represent the octal 1 out of 8 speed. So here, they are representing the opposite value of the position. So here it will be the negative power of 2, 2 power minus 1, 2 power minus 2, 2 power minus 3. Whereas 2 power 0 will be always 1. So here we have the opposite or negative value of power 2. So the binary number 111.111 is along the top. Under each bit is its denary equivalent. For example, the leftmost binary one has a denary equivalent of 8 or 2 power 3. This means that the binary number 1000 would be equivalent to 8, as we have 2 power 3 will be 8. And 1000.000, this also will be 8 equivalent to 8, as all the zeros will be no decimal places. As we move to the right, the value of each number, whether binary or ordinary, is halved. So we will halve the value of power 2. The value of each binary digit is determined by its position in the series of digits. Each move to the right halves its value. The process of halving continues after the point symbol, giving value of half, quarter, 1 out of 8, which is 0.5, 0.25, 0.175. The bottom row shows that these numbers can also be represented respectively 2 minus 1, 2 minus 2, and 2 minus 3. Here we have a number, and we want to measure its value, how much it's equivalent. We have a binary number, and we want to see how much the decimal number equal to this binary number. So we have 1111.111. So here the first one is 2 power 0. The second one, if we go left, here 2 power 1, here is 2 power 2, here is 2 power 3. So if we starting from the left side, we have 2 power 0, 2 power 1, 2 power 2, 2 power 3. Then after the decimal point, we have the 3 ones here, which is the equal to the negative power of 2. So here we have 2 power minus 1, 2 power minus 2, or 2 power minus 3. So here we will put the equal number 1 plus 2 plus 4 plus 8, and after on the right side we have half plus quarter plus 100.125. So this will be equal to 15.875, which is the denary number. We can calculate any number, any binary number in this way. Remaining with the idea of environmental monitoring, suppose that an agricultural application for the Internet of Things required the wind direction to be monitored as well as speed. So if we need also to measure the direction in which way the wind is going. Conventionally, wind direction is specified by whether the wind is blowing from. So for example, a southerly wind blows from the south to the north. The only way we can represent wind direction with a digital remote sensing station is a binary number. So we have to add one more binary. We have to add one more bit to represent the direction of the wind. So how we can do this? If we want to represent the direction of the wind from where it blows, this means we have to add 0 binary, and if it's blowing from the south, and if it's blowing from the north, we will represent it by 1. So the speed of the wind can be represented by a different binary number in the way it's described earlier. So we will have 000 if it's from north, or 0 from its south, and if it's from west, it will become 110. If it's from east, it will become 010. So we will need to represent the different direction. 111 if it's northwest, 001 if it's from northeast, and the same things with southeast and southwest. Throughout the wind direction example, it's assumed that all wind direction readings use the same number of bits. So we will use 3 digits for representing the direction of the wind. This is called the fixed length coding. An alternative to fixed length coding is variable length coding, which we have different bits number to represent the direction, where not all codes have the same length. So here we could have, for example, 0 to represent only the westerly, 10, 2 digits to represent the southerly, 3 digits to represent the easterly, and 3 digits to represent the northerly. We could have different code to represent the direction. Okay. Radio communication. Radio is particularly subject to a problem that don't affect communication via other media, such as wires or optical fibers. For example, we have the radio signals can interfere with other radio devices and devices that generate interference as byproduct of their normal working. For example, if they are working on the same frequency, this means we could have two signals interact and interference between each other. This will increase the probability of errors, and the stronger the interference, the greater the probability of errors. So we could have a bit error occurs when a transmitted 0 is interpreted by the receiver as 1 or vice versa. So if we receive it as 1 and it was 0, or the other side. So we already highlighted the meaning of interference, and we said covers many unwanted intrusion on a wanted signal. For instance, when you listen to a radio and you listen when you stop on the traffic light, you hear another signals coming from the nearby cars. This means you have some noise coming from around. Another potential problem with radio is also blockage of the signal by obstacle. So if you have different buildings, different materials around the signals also, this means the radio waves are blocked by a building. So there are some barriers to the transmission of the signal. Licensed and unlicensed spectrum, potential problem for Internet of Things application and all radio communication as they use the radio signals, is the limited availability of suitable radio spectrum. The band for spectrum exceed availability. All radio transmissions occupy space in the radio spectrums because all the devices will have to use some frequencies and somehow. Here we have some transmission and Wi-Fi frequency band, so they use the Wi-Fi band to transfer the radio signals. The amount of the frequency band occupied is called the bandwidth, how much it's occupied from the bandwidth of the signals. The term is also used to refer to a channel's capacity for carrying data. So here, if we have a 20 megahertz bandwidth, how much data it can carry on. We have the central frequency, so all the signal strength will be in this range. Short range would typically be a range of meters or a few tens of meters. Short range would cover a few rooms in a building. Wi-Fi is the most common example of short range wireless. Medium range would be several tens of meters up to a few kilometers. Long range would be from a few kilometers upwards. So this is some of the features of the Wi-Fi signal. Here is some examples about different technologies using different range of radio communication. So what can be the medium range and what is the long range? And also what is the short range of different communication. So for example, if we have here Bluetooth, we have short range, only the signal can be transferred only between meter to 100 meter. If we have cellular mobile, it will become from 100 meters to a few kilometers. If we have point-to-point fixed link, we could have tens of kilometers to hundreds of kilometers. In the future, the Internet of Things will be used in the 5th generation communication, mobile communication. This will enable more things to be communicated with each other wirelessly by using different networks communication like the cellular communication, and will allow more invention in the future. So in summary, we have looked about converting binary numbers with a binary point into a binary number with decimal point. We have determined the numbers of bits required to provide binary label for a given numbers of entities or states. We have applied binary numbers as labels for entities or state, and we have seen explanation of basic aspects of the Internet of Things. And we have discussed some of the issues regarding the infrastructure of the Internet of Things. And we finish meeting 12. Thank you very much for listening. If you have any question, I'm happy to answer it.